Today we're going to talk about exponential growth and decay. Exponential functions have the form y equals a times b to the x, where a and b are constants and x is our variable. As long as, and a has to be positive. If our b value is greater than 1, then the function is a growth function, an exponential growth function. If our b is some number between 0 and 1, then the function is an exponential decay function. So, this question asks us to tell whether the function represents exponential growth or exponential decay, and then graph the function. We can see in this function we don't have an a value, but our b value is 3. Since 3 is greater than 1, we know that this is an exponential growth function. To graph it, we just make a table of values. So we're going to use -2, 3 to the -2 is 1/9. -1, 3 to the -1 is 1/3. 0, 3 to the 0 is 1. 1, 3 to the 1 is 3. And 2, 3 squared is 9. Then we can graph our function. Notice that we're never actually touching our x-axis. We're just getting infinitely closer to this, because any number raised to an exponent will never give us 0. So that is what all of our exponential growth functions look like. This function is exponential decay because our b value is 1/2, which is between 0 and 1. Once again, we're just going to make a table of values. Alright, so we're going to use -2, -1, 0, 1, 2. 1/2 to the -2 is 4. 1/2 to the -1 is 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 squared is 1/4. Once again, so we're going to go to graph it. -2, 4. -1, 2, 0, 1, 1, 1/2, 2, 1/4. So notice that our exponential decay function goes the other way, but once again, we'll never actually touch the x-axis. The population P in thousands of Austin, Texas during a recent decade can be approximated by this function, where T is the number of years since the beginning of the decade. Is this exponential growth or decay? We know that it's exponential growth because we have 1.03 as our b value, and that is greater than 1. The next question asks for the annual percent increase or decrease. The answer to this is 3%. Our term that's raised to the power is, if it's a growth function, is 1 to the r, 1 plus r. And if it's a decay function, it's 1 minus r. So we know that 1.03, since this is a growth function, equals 1 plus r, where r is our rate of change. So that's 0.03, which is simply 3% increase. The next question asks us to estimate when the population was about 590,000. So we're going to write 590. Remember that this is already in terms of thousands. Equals 494.29 times 1.03 to the t. Now, we can't solve for exponents yet. So what we're going to do is simply graph and estimate. So you can plug the original function into your calculator as y equals 494.29 times 1.03 to the x. And then when you get your graph, you can simply hit the trace button and trace along the line until you find out where y equals 590. This should be at t equals about 6 years. Make sure that your window is large enough to accommodate y values up to 590. You might want to make it even larger than that. This problem says you take a 325 milligram dose of ibuprofen. During each subsequent hour, the amount of medication in your bloodstream decreases by about 29% each hour. Write an exponential decay model giving the amount y in milligrams of ibuprofen in your bloodstream t hours after the initial dose. So we have y. And then our A value is always our initial value. So our A value is 325 because we started with 325 milligrams. Now, our change factor right here is going to be, because it's decay, it's going to be 1 minus 0.29 because it's 29%, and then to the t. So we know that y equals 325 times 0.71 to the t. Now, it asks us to estimate how long it will take for you to have 100 milligrams of ibuprofen in your bloodstream. Once again, we can plug this into our calculator and trace until we get y equals roughly 100, and that's after roughly 3.4 hours. The number y of duckweed fronds in a pond. This lovely picture is duckweed fronds, in case you didn't know what those were. They're little plants. After t days is given by the function here, where a is the initial number of fronds. By what percent does the duckweed increase each day? Now, to figure out percent, we look at our number that's raised to our variable, but in this case, our number, 1230.25, is raised to the t over 16. Now, that's not raised simply to our exponent, so we need to use our exponent rules to simplify. So we can do 1230.25 to the 1 over 16th power to the t. Because power to power, we can multiply our exponents. So this is the same thing as this. So then we can just punch this into our calculator. 1230.25 to the 1/16th is roughly 1.56. So then we have 1.56 to the t. Obviously this is growth, so remember 1 plus r equals 1.56. Our rate of change is 0.56, or 56%. The last problem involves compound interest. This is the formula for compound interest. Your initial principal amount is P. That's the amount of money that you put into your account. Your annual rate is R, written as a decimal. So if it were 6%, you would write that as 0.06. Compounded is how often they give you your interest, and this is in times per year. This is our n value. So if it was compounded monthly, this would be n would equal 12. If it was compounded semi-annually, n would equal 2, etc. Our time period in years is t. So if it's 5 years, t equals 5. If it's 6 months, t equals 1/2. And then amount in account is A. So in this problem, we started with a principal of $8,600. Our R is our annual rate. Remember, we have to write this as a decimal, so it would be 0.0132. N is the amount of times it's compounded yearly. This says it's compounded quarterly, which means it's compounded 4 times in a year. T is the number of years that we leave it in the bank. This is also 4, so it says it's in the bank for 4 years. And A is what we're looking for. So we can write A equals 8,600 times 1 plus 0.0132 over 4 raised to the 16th power, because that's n times t, which is 4 times 4, which is 16. Now when we do this, we get $9,065.49.